Okay, GM. Hey everybody, I'm Devan Mitchem from Google Web3.
I'm Christoph from Flashbots, and this is joint work also with a bunch of Flashbots mates that you can find there.
Yeah, thanks for joining us on this session on this hot day here. Yeah, we have this is a big team effort, a lot of names on here, a lot of folks to look into and follow. We're going to dive into the dark forest on public cloud, and we have 3 parts in this session. Part 1, actually we're going to jam all this in 20 minutes. So after 20 minutes, you're going to come out expert in physical networking and everything you need to know about Ethereum networking. So the first part will cover the physical flow of bits across the internet. Part 2, we'll talk about how those bits go from various internet locations into the Ethereum supply chain. And then third, we have a couple call-outs for areas for further research and some recommendations. And then for those that are into data science or open source components, we have a data notebook that we created that you can use to look into the numbers behind us and hack and remix some of the data that we came up with. So let's talk about the physical layers. So this is how the internet is basically built. This is how the tubes are built. You have the local last mile on the left. These are typically aerial fiber cables, copper lines, high voltage power lines, where the top line is typically aerial fiber, and then internet exchanges that are in most cities. And then on the right, you have effectively how these bits then travel from the various cities into the ocean across continents. And if you zoom out, here's a map on the left of the submarine cable systems that span the globe, right? And you can see these are all physical cables dropped into the ocean that follow certain paths, navigable paths. And on the right, these are the virtual networks built on top of the physical networks. And in today's talk, we're going to talk about how latency on the right and geography on the left are actually not really one and the same. And there's some important nuances you should understand as you're building apps, as you're designing mechanisms, or as you're building and solving for users. So when it comes to geography, right, so again, internet paths might not be the best in physical path. And the one thing to understand is that ISPs are actually very large local area networks, okay? And you have to understand the relationships that ISPs might have between one another. Some ISPs might be smaller, might be regional ISPs. Other ISPs might be transcontinental, right, where they have deep networks in the major tier 1, tier 2, tier 3 cities. And so it's important to understand the business relationships between ISPs because that often determines the path. If you're interested in this topic even further, you can look up autonomous systems, BGP in terms of routing. But again, what's most important here is the paths your packet take really depends on this connectivity, which might not be fully understood. Now, what does it mean for Web3? So on the right, it's often that you see this case called tromboning, where you might have packets that you think might go one direction, but in fact they go another direction. And we have some data here to share in terms of what that looks like. One other thing to note for folks that might trade on centralized venues and also trade on decentralized venues, it's also important to note that location matters. And Christoph will get into some of the details. Quick shout out. So one example in terms of how at least we at Google Web3 have some experience in terms of both the Web 2 form of internet routing and Web 3 is we actually operate a faucet. You can go to this page, you can scan it, you can get a drip for Ethereum testnet and others. But generally the way this works is when you scan this and you get a drip from Google into your wallet, a couple things happen on the left. I'm not going to read all these, but in short, your request goes over some radio towers, it goes into some backhaul metro fiber, it'll bounce around your ISP. Depending on your ISP's relationships, it'll bounce to other ISPs. It goes under the ocean or it goes over the mountain ranges and eventually lands on Google Cloud. And then from Google Cloud, we dump that into a testnet from one of the nodes we might have running on Ethereum testnet, land that in a testnet mempool, testnet validation, then it gets gossiped out, and then all the way back in terms of whatever node your wallet's reading from to see that that actual drip came in. So there's a lot happening, right? Things in white are the physical layer. Things in gold here are the Ethereum testnet layer. Now, here's a study. All the raw data is available on the top right if you want to scan this. This is some data that we took out from this thing called the Perf Kit that Google developed, where we have VMs in every single Google data center constantly running pings between different locations, right? And we built this map from Tokyo to understand, okay, from Tokyo, how long does it take to get to different regions? And if you note, there's an interesting trend here. When it comes to connectivity, Tokyo to Virginia is much faster than Tokyo to Europe. It's interesting. And this matters, right, in terms of maybe your design. And it's important to know, right, when it comes to that decision, if you even dig into the data deeper, it actually turns out from Tokyo, it's actually faster to get to the US West Coast and US East Coast than it is to get to Europe, Frankfurt, and Amsterdam. Now, why is that? You have to follow the tubes. Okay, it all depends on, again, those maps that I showed you before and the routing. So putting it all together on the left, these are the tubes in terms of why it matters, in terms of your connectivity, and then how it lands into the RPC and mempool. It's all somewhat related here. We have further data here on the talk. If anyone's interested from a data science perspective, we have a lot of this data on Google's BigQuery public data sets. We have a notebook available that's up there. We also have some feedback and some ideas to share below. But with that, I'll hand over.
Awesome. Right, another plug, so mempool dumpster, which is quite comprehensive data set of public transactions in Ethereum, is you can now also query on BigQuery instead of what else you do, Dune or whatever. You can also work on it with Google products. And I think it's a nice sort of avenue for research to think about this connection between transaction data and latency data. And I give you some ideas. Most of that is actually due to research from other Flashbots people. Shout out to Data Always, to Burak, and so on. And that should give you some idea how latency matters in many different ways and how geography matters in many different ways in Ethereum. So this is a chart that probably many of you are familiar with. It's the rise of private order flow, right? So it is true that if you don't have access to a certain kind of order flow, which is sort of exclusive to block builders, then you cannot build that profitable blocks, right? That is a vector of centralization. It's a vector of centralization that is quite visible if you compare that to people who build their blocks locally, right? Basically on public data. So if you have access to this kind of private order flow, you can pack your blocks with much more valuable transactions, and you can generate more profit from that. Okay, and there's a clear trend in the data, and all of that has to do to a certain degree also with connectivity. Another touch point where sort of latency matters is how fast your transactions are included in the blockchain, and that depends on sort of which nodes see it and which nodes distribute it. For example, Bloxroute has this distribution networks of different. So they have a relay, but also they have proxies where they quite quickly distribute transactions that they see over the network. So if you distribute a transaction over Bloxroute, it will get on average, and also in the long tail, much faster into sort of the P2P networks than if I got it from my node in Zurich at my home, right? And it would be even worse if my home wouldn't be in Zurich, but in, I don't know, Buenos Aires. Okay, so there are differences in the nodes. Nodes are different, right? We treat them as the same from the point of view of the protocol, but not all nodes are the same. Here are some nodes. This is data from a robust incentive group. Sort of gives you an idea of where Ethereum validator nodes are geographically located. This is a question mark. I don't know whether that is sort of broadly distributed over the world. Certainly there is like a majority of these nodes in North America and Europe, definitely. And there are nodes lacking for sure in places like Africa and in South America and India, right? If you compare sort of population density with node distribution. And that has to do with infrastructure, that has to do with latency. If you look at the layer where blocks are built, I don't know whether you know that, but basically relays are in two places, right? They are in East Coast America and they are in Europe. Those places are the places where blocks are actually produced, right? In some sense, because builders tend to co-locate with these relays, right? So the network is, in some sense, everybody sends a transaction to these two red dots, right? Why these two red dots? And that has to do with the entire infra, right? So those two red dots are connected by very fast connection through this transatlantic fiber corridor, where you basically have very fast connection between Europe and North America. And you wouldn't have that if, I don't know, you run your relay in, I don't know, Nigeria, or if you run your relay in Buenos Aires. It takes longer, okay? So there's this correlation between infrastructure and where our infrastructure for Ethereum that we use is located. Sort of is dependent on history, right? History is influencing infrastructure. Infrastructure is public infrastructure that we're using, public or private infrastructure that we're using, and that shapes Ethereum, even though we maybe wanted to build something completely different. Okay. Another way in which latency enters, that's again beautiful data by data always, shout out, is in this bidding data on the MEV boost relay. So if you compare over time how frequently bids in the MEV boost relay are updated. MEV boost is the market in which blocks are proposed to Ethereum. So we bid on who produces the highest value block. And there is as you compare these curves over time, bids are updated more and more frequently. What does it mean? It must mean that people have the infrastructure to update those bids more frequently, right? So they must sit close to the auctioneer, the relay, and there is a vector of centralization. It is a vector of centralization. I not only claim that, it's visible in the data, right? Until January of this year, basically the market was a duopoly almost by two big builders being co-located with these relays, okay? So those are facts that are sort of shaped in some sense by infrastructure, even though we wanted to build maybe something different. So that is data on bidding in MEV Boost and on distribution of relays. Another fun thing that you can do, that's a project that our intern at Flashbots, Senyan, is currently pursuing. You can take this latency data that Google Cloud provided us, and you can run simulations in how certain kind of games play out in Ethereum block production infrastructure. For example, timing games. I don't know whether you've heard about them. So people trying to delay propagation of blocks to build more valuable blocks. You can wonder how that extra value is shaping sort of the location of nodes in the network. And they built this nice simulation tool. I don't think it matches reality yet, but you have this sort of nice way of feeding in the data, latency data, and you see the convergence of nodes clustering, right? Because there is a benefit of being close to certain kind of nodes. There's a benefit of being close to the relay. And there is a benefit of being close to each other. Okay. That's one way of how you can use this data set. Other questions that you can ask, I just give you a bunch. It's not comprehensive. We have another plug. We have a research database in Flashbots with some of problems that we're interested in, and we look for people collaborating with us on these questions. So some of the high-level questions that I'm interested in or would find interesting to hear about research that other people are doing is this entire, influence of location or connectivity on what different people do. So what does it mean, for example, for users, right? So you cannot be a high-frequency searcher if you're located, I don't know, in Cannes, right? Doesn't work for you. You have to be co-located with a relay, right? But it also matters for sort of other kind of use cases, right? So your user experience is shaped by by where you are located in the world, by your connectivity. You sort of experience, user experience as a validator. I don't know whether we call them a user, but validator experience looks different in different regions of the world. How easy it is to run a validator. How much profit you make from running a validator, right? Uptime and these kind of things. You miss maybe attestations and these kind of things. We could wonder, okay, what happens if you change the system? There's discourse around reducing slot time. I mean, there's benefit from that, right, reducing slot times, but it affects people asymmetrically, right? It doesn't affect everybody in the same way. And so you can think about these questions. Ethereum is not an island. It interacts with L2s, right, which also servers. And you're wondering, okay, where are the servers located? Usually also Europe or North America. Or you have perp DEX, the centralized exchanges, usually in Europe or more of them in Asia, Binance in Tokyo and so on, right? I can wonder, how does this infrastructure interact with Ethereum? And why does the network structure looks like it? You can do event studies. That's another idea that I had. Okay, you could wonder, okay, maybe you've heard that some, or you've discovered in the data that some roll-up has moved the server somewhere else, and then you can figure out what does latency do to what people are doing. You can do also more like research of the practical research of the kind. Okay, how hard or how easy is it to run critical infrastructure within Ethereum in different places in the world? We have very little knowledge about that. And finally, the bigger question is, okay, how can we make location matter less? All of those, there are probably more ideas, right? But all of this you can answer with a mix of data and probably good ideas, and I wanted to encourage you to look into that. Final slide, and maybe most important slide. Maybe the question 0 that you should ask before you ask all of these questions is actually, what do we want? So I've redrawn the previous validator relay map in some way. I added, I don't know, just for fun, a relay in Buenos Aires. Right, we will all be there in, I think, November. So we should have a relay there. I removed 40% of the nodes in North America and Europe. I don't know whether you've noticed. There were too many, so you can remove 40% without, changing this picture. I added a bunch of in Africa and so on. I don't know whether that's a map that we want to have, but we should ask the question, okay, what kind of map do we want to have? And sort of, it's shaped by infrastructure, as we have learned, but history is not everything, but there are also, memes and ideas that we want to follow, right? So we want to have an idea of how this map should look like. We should have a vision of how this map should look like. And if we can build it with current infrastructure, with Google and whatever, with internet service providers, good. If we can hack that, but if we cannot do that, then we should find a different way. Because we don't want to replicate the same kind of map that we have, right? That's it. Any final words?
Yeah. So if you found this topic interesting, definitely reach out. Again, we have a Notion page on the top right. You can hack our data on the bottom right. We're around. If you want some Google slushies in the back, happy to grab a slushie as well. So thanks for your time, and thanks for joining us.